Someone is praying for you. Someone is praying for you. So when it seems you're all alone and your heart will break in two.
Welcome to our lessons on ordinary differential equation. We are still on solution to homogeneous differential equation with constant coefficient. In our previous lesson, we looked at the equation whereby the characteristic equation has repeated roots. In this lesson, we are looking at where the characteristic equation has complex roots. So if you consider a second order equation for simplicity's sake, so we are just considering this equation, and has a complex root of alpha plus I beta, where I squared is -1. Do not forget that this one is going to have two roots. That's alpha plus I beta and alpha minus I beta. Because the characteristic equations and their conjugate will be present. And none of them will be repeated since it's a second order. So we have the lambda 1 to be alpha plus I beta and lambda to be alpha minus I beta, where alpha is a real part and the beta is the imaginary part of the complex number. Now with this root, we say that our solution will be C1 e raised to the power alpha plus I beta x plus C2 e raised to the power alpha minus I beta x, which is similar to what we have been doing so far. But we don't want to leave our solutions in complex number form, so we want to do a little bit of expansion and simplification. So you're going to get C1 e raised to the power alpha x times e raised to the power I beta x plus C2 e raised to the power alpha x times e raised to the power -I beta x. And we can factorize the common factor here, which is e raised to the power alpha x. And this will be multiplied by C1 e raised to the power I beta x plus C2 e raised to the power -I beta x. But we know from our knowledge in complex numbers, if you want to write the complex numbers in polar form, e raised to the power I beta x is cos beta x plus I sine beta x. And then e raised to the power -I beta x is cos beta x minus I sine beta x. So if you substitute this once here into this equation, then we are going to have for y of x to be equal to e raised to the power alpha x multiplied by C1 times cos beta x minus plus I sine beta x plus C2 multiplied by cos beta x minus I sine beta x. And if you decide to group lie types in cos of cosine and sine, then we can say that this is going to be C1 plus C2 cos beta x plus C1 minus C2I sine beta x. So this is what you're going to have here. Now if we let K1 to be equal to C1 plus C2 and K2 to be equal to C1 minus C2 multiplied by I, then we can write the general solution as e raised to the power alpha x K1 cos beta x plus K2 sine beta x, where our K1 and K2 are constants. Let's pick an example. You have to find the general solution of d square y by dx square minus 6 dy dx plus 25y equal to 0. As usual, the characteristic equation is lambda squared minus 6 lambda plus 25 equal to 0. If you solve this one, you're going to get lambda equals to 6 plus minus the square root of 36 minus 4 times 1 times 25. The whole thing over 2, which is going to give us 6 plus or minus the square root of negative 64 over 2. So you're going to get 3 plus or minus 4i. So the lambda 1 and 2 is simply 3 plus or minus 4i. So here, alpha is the real part, which is 3, and beta is the imaginary part, which is 4. So the general solution is going to be e raised to the power 3x multiplied by c1 cos 4x plus c2 sin 4x. Please don't get confused when I brought c1 and c2 instead of k1 and k2. You simply mean they are constants. So that is the general solution to this equation. Let's look at the second example. We have to find the general solution to this, and we have to also determine the solution when the initial quantity y of 0 is 2 and y prime of 0 is 3. So as usual, the characteristic equation is lambda squared plus 2 lambda plus 2 equal to 0. And when you solve, you're going to get negative 1 plus or minus I. So alpha is negative 1, beta is 1. So the general solution is e raised to the power negative x times c1 cos x plus c2 sin x. So now we start using the initial conditions. Y of 0 equals to 2 means y of 0, when you put the 0 here, you're going to get 1 here, you're going to get 1 here, you're going to get 0 here. So you are left with c1 equals to 2. So therefore we can say c1 is 2. Now to use the second condition, which is y prime of 0 equals to 3, because this is a derivative, you must differentiate the general solution. So we look for y prime of x, and here we use product rule. We hold this and differentiate this, and that will give us negative e raised to the power negative x c1 cos x plus c2 sin x. Then plus, we now maintain the e raised to the power negative x and differentiate this. If you differentiate cos x, you get negative sin x. So you get negative c1 sin x, and if you differentiate sin, you get cos x, so plus c2 cos x. So now when you put in the initial condition as 0, this is going to be 1. So we are going to have 1 here, and this will be 0. So you are going to get negative 1 c1. So negative c1. When you come here, this is going to be 1 again. This is going to be 0, but we're going to get 1 here. So we are going to get plus c2, and it's equal to 3. So c2 is 3 plus c1. But c1 is 2, so become 3 plus 2 equal to 5. So c2 is 5, c1 is 1. So therefore, our particular solution here is u raised to the power negative x. c1 is 2, so 2 cos x. And c2 is 5, so plus 5 sin x. Let's look at the third example. So here, the characteristic equation is going to be lambda to the power 4 minus 8 lambda cubed plus 42 lambda squared minus 104 lambda plus 169 equal to 0. And if you factorize this, you're going to get lambda minus 2 plus 3i squared times lambda minus 2 minus 3i squared equal to 0. So we are going to have lambda to be equal to 2 minus 3i and lambda to be equal to 2 plus 3i. So this is having a repeated root of multiplicity 2, because each of them occurs twice. Alpha and the beta. So alpha is 2, beta is 3. So we are going to apply the repeated root method plus a complex root. So we are going to see that our y of x is going to be e raised to the power 2x, because alpha is 2, multiplied by c1 plus c2x cos 3x. So c1 is for the first root, second root, the repetition, then plus c3 plus c4x sine x. So this is the general solution. And what we do here is that since it's a repeated, we have multiplicity of 2, we apply the method that we learn from the repeated roots inside against the constant, all of them multiply by that. Thank you for watching, and we will meet again.